All voltage is also equation of P5.
Sometime if you have to measure a magnetic flux density or magnetic field in an experiment, you have to use Hall probe. It is not a topic completely related to Hall probe or like paper 5, but sometime if you have an experiment where you need to measure magnetic field or magnetic flux density, in that case, you have to use a Hall probe. And
Just a
remember,
mechanism, right?
it is a Hall probe is a device. Hall voltage is a voltage, and Hall effect is a phenomenon.
Okay.
Okay. Hall's effect. So I have to make a diagram here.
Excuse me, sir.
Yep.
Sir, could you upload the studies class link? Like there was some internet issue over here, so I couldn't hear all.
Okay. The thing that I'm trying to show over here is that there is a north pole of a magnet on the top, there is a south pole of a magnet at the bottom, and there is a piece of metal in between. Does this look like what I'm trying to show over here?
Yeah, yeah, sir.
Yeah. So on the top and the bottom, we have a magnet, and in the middle, we have metal conductor. And there is a current that is now trying to go in this metal conductor. Do you remember that when we did first we put a conductor in a magnetic field and observe what happens to the conductor when current passes through it, and we know that there will be a force. Then I told you that we will be doing a free charge particle that enters the magnetic field. What happens to the free charge particle? We understood that. Now we are getting to the third level. We are again putting a conductor in a magnetic field, and this time we are using a wider conductor with a thinner uh, height. What happens is electricity, when charge particles move through the conductor, because of the force that acts on the charge particles which are moving through the conductor, the charge particles start to develop, they start to drift on one side. So what happens is uh, sides of the conductor start to develop an electric potential. Look, we know if this is the current, it means it is the positive charge particles direction. So this is the current. Because of the magnetic field, current should experience a force to that direction. Okay? There should be force on the current to that direction. Okay. If you make your fingers from north to south and your palm is giving you the direction of the current, you will see force will be to the far end of the metal. So what will happen? Because of this side should start becoming positive and this side should start becoming negative. You know why? Because the charge when moves in a conductor, it is having a drift on one direction. It is having a kind of push to one side. That will make positive charge go on one side, that will develop an opposite charge on the other side, and then we can experience, or we can actually detect a potential difference between the two sides of the conductor. And it is not the front and the back of the conductor, which is normally there is a potential difference that makes the current go, but it is the potential difference that is developed on the sides of the conductor. Now, as I usually do, first I try to explain it in a 3D diagram, and then we go back and make a 2D diagram. So let's say this is the conductor. Okay.
Hello, sir.
Yes. Okay. The magnetic field downward. So B is into the page right now. Current is coming this way. So what should happen is positives towards. So this side should start developing
Yeah, sir,
positive
your voice
potential.
is
This
lagging
side,
quite a bit.
just one second. So listen, if current is coming this way, current is the direction of the positive charge. So when positive charge is moving this way in a magnetic field which is into the screen, it should experience a force in upward direction. So upper side should gradually start developing a positive potential. So if the upper side is becoming positive potential, the lower side is gaining negative potential, and it is something which is developing with the passage of time. So what will happen? There will be a time that electric field will become so strong that this current will start flowing in the like unaffected because of the magnetic field or electric field. Now, there is positive potential over here. There is a negative potential on this side. This potential difference is called Hall voltage or Hall's voltage. Okay. This potential difference, which is developed across the sides of the conductor, is known as Hall's voltage. So examiner can make different kinds of diagrams, and one very common diagram is that examiner makes a cuboid like this. So this is a cuboid, and examiner says there is a magnetic field in upward direction. This is magnetic flux density. Okay, this side is called top. There is a side which is called bottom over there. This is front. There is a side which is back. This is the right side, and there is a left side. When there is a current which is passing in this direction, this is the direction the current enters the conductor. Okay. Which two sides should actually develop this potential difference? Will the potential difference be developed between front and back, top and bottom, or left and right? That will be between the left side and right side. Okay. And why is that? Here is something that will help you to solve this kind of question in exam. Hall's voltage is developed um, perpendicular to magnetic flux density as well as to the direction of current. So Hall voltage is developed between left and right. But in exam, you don't have to use left and right over there. He gives different kinds of name to the side. Like every vertex is named as A, B, C, D, E, F, G. So you have to write the whole name of the site, like it is C, D, G, H, and A, B, C, D. That kind of names are used. Now, here are the things that you have to understand. The magnetic flux density here is B. This side is the thickness, so it will be T. First time in physics, we will be using small t for something else. So pay attention. In this case, t is not time, it is thickness. Okay. This side is this is width. Let's give it name W. So this is area, which will be WT. Okay. Now remember, this length is W. This length is what? W. The potential difference between top and bottom is Hall voltage. So this Hall voltage at a distance W should develop a should develop an electric field. See, when current starts moving in the right in the straight line, it means the force because of the electric field is balanced VQV, where V is the speed, the drift velocity. So here we go. When current is straight, electric force is equals to magnetic force electric forces, EQ, magnetic forces VQV. So we can clearly see the Q becomes irrelevant, and we have E equals to BV, where E is potential difference over distance, and in this case, potential difference is Hall's voltage. We call it VH, and distance is W. Between the sides which develop that potential difference, the distance is W. That will make E Hall voltage over W equals to VV. So VH Hall voltage, first formula, BVW. W is the width of the conductor. Okay. So this is the first form that we develop over here. Okay. Sometimes we also use VH equals to BVD. If you don't want to use that W over there, it is also VVD. Now, let's move on. Hall voltage equals to BVD. Sorry, BVW. But remember, charge particle is not moving freely. It is moving in a conductor. Such motion charged particles in conductor, they drift. Just 1 second. Speed of moving charge in a conductor is called drift velocity. If we go to the graveyard of our memory, we will find drift velocity in the syllabus of AS, where we did drift velocity equals to current divided by N A Q, where V is drift velocity, I is current, A is cross-sectional, area, A is cross-sectional area. In this case, area is WT, which is W is the width, T is the thickness. Q is charge on each charged carriers. Sometimes, most commonly, if it is a conductor and a charged particle is moving, Q is equal to E. Okay. Where E is elementary charge. Where E is elementary charge. E equals to 1.6 into 10 to the power minus 19 coulomb. So let's fit this thing into the above formula. Hall voltage is BVW and V equals to I over ANQ. I need a formula of Hall voltage that does not have W in it. So let's start. First of all, I will make current. The drift velocity is replaced with its formula. So Hall voltage will become BIW over ANQ. Oh, I did not mention what N is. I made the whole list because everybody knows what Q, A, and I is. The only thing that was important was what is N? Normally, we think that N is a number, but in this case, N is not a number. It is charge density or number density. N is number density. N is number of charged carriers divided by volume. Okay, and its unit is per meter cube. So there we go. This is the formula. But I need a formula that does not have a W in it. So let's see what I do. I know area equals to WT. So Hall voltage becomes BIW over WT and Q. And I think you can see that W becomes irrelevant. And here we have the formula for Hall voltage. BI over NTQ. Remember, this is magnetic flux density and measured in Tesla. Current in conductor measured in amperes. Charge on each particle. is not time, remember, it is thickness and must be in meters. N is number density or charge density. And unit is per meter cube. And this is Hall's voltage, and its unit is volts. Any confusion? Field or magnetic flux density at a particular point around a magnet or between a coil or any other place, we need to know how strong a magnetic field is. We use this thing. This is known as a Hall probe. We just put it in the magnetic field. It will develop a potential difference. We can measure that potential difference and then can convert it into magnetic field density. For that, we need to have current, and like we need to know what current is moving through there in the Hall probe. What is the material used? What is the number density of that material? How thick is the material? And what is charge on each particle? We cannot change the size of the charge. Size of charge is constant. So if like this Hall voltage is not like in volts, or it's not a very large voltage. It is very minute voltage, sometimes in millivolts, sometimes smaller than that. So if you want to make the value of Hall voltage more detectable, so if we need to make value of Hall voltage large, so we can easily measure. We can, number one, use larger current. Use a material with lower number density. Semiconductors. Do you remember that to measure this Hall voltage, we had to put this um, conductor in between the magnetic fields? Okay, we did that. We put a conductor in between the two magnets to develop that Hall voltage. So the material of the Hall voltage matters, like what material we use. If we use copper, copper will have a very large N. So if we use copper as the metal or conductor over there, the value of Hall voltage will be very, very small. So if we use iron, iron is a conductor, but it is not as good conductor as copper is. It has a smaller value of N. So the potential difference will be larger. But if you make it very, very large, the best thing is semiconductors, because they have very small number of N and they can develop a very reasonable sized Hall voltage, and we can easily measure it. So if you want to make Hall voltage value bigger, you can either use a larger current or you can use a material which has a smaller N. Example, semiconductors. And the third thing that you can do is make the slice thinner. If the slice will be more thin, it will develop more potential difference, because you can see that the thickness T is in the denominator. T and Hall voltage are inversely proportional. If you make the T smaller, you will make Hall voltage larger. That will help you to make the value more measurable. Or you can use a material with smaller N semiconductors, or you can use a larger current. So we are done with the Hall voltage. Tomorrow we will be starting, like in the next class, we'll be starting with electromagnetic induction. Okay, this will be our next lesson. Till then, take care.